Okay, in this video, we'll be looking into a pattern that can be used to quickly differentiate any power of x. But first we want to revisit a derivative we have seen before in a more visual way, for two main reasons. One is that often a picture helps us further understand what's going on a little more, and second, because it gives us a way of approaching derivatives that can be useful for more complicated situations later on. So we have x squared, which we're going to visualize literally as a square of side length x. Then x squared measures the area of this square. Then the idea of a derivative was to push the x the tiniest bit across, and then to see how the y value responds to that change. So we're going to increase the x by a tiny bit. Now in the past we called that a little bit h, but we can sort of look ahead a little bit, understanding that in just a moment we're going to limit this distance to 0, and so we'll just jump ahead and call it dx right off the bat in this case. Again, standing for that tiny push to the x value that will eventually limit to 0. Notice, of course, if we push the x across by a bit, then both dimensions of the square have to get affected. So the new area has these new pieces here. And our aim is to see how the y value responds, and so the change in area is what we want to measure. This change will be primarily made of these two rectangular strips here. And we might be worried about the corner piece as well, but in the limit as we send dx towards 0, the contribution of that piece will vanish as well, will go towards 0. And I'll leave it as an exercise for you to look back on the proper algebraic derivation of this to see if you can locate where this little corner piece sits in that working, because it does feature as one term of the algebraic mess we did back then. Alternatively, just include it if you want in this calculation, then see what happens as we send dx to 0 to convince yourself that we can safely throw away that corner piece. Anyway, back to the rectangular strips then. The tiny width is of course dx, the long height is just the x value, and so each strip has area x dx, which when added together gives 2x dx. Remember, this resulting change in area is exactly what dy measures. And so from this, we recover the thing we got before, that dy dx is 2x. Now the cool thing is we can do the same thing with x cubed, even if we haven't done this algebraically, and honestly it would start getting quite messy to do so. I won't work out the details in full, I'll let you fill in the gaps if you need to. But we can still start by drawing a cube of length x, and now x cubed measures, of course, the volume of this object. The key point is if we push the x value up by a bit, the volume will essentially increase in the form of 3 thin slabs that have been glued on, one for each dimension that we've increased the x value in. So they would account for the increase in volume. Each slab would have volume x squared dx that comes from multiplying the face area x squared with the thickness dx, giving a total increase then of 3 lots of x squared dx. Once again, this resulting change in volume is our dy, and from this we get that dy dx is actually 3x squared. Now we want to extend this to any power of x, and obviously we can't draw any higher dimensions. Cubes like 3 dimensions is our spatial limit. But reviewing what we've done before, there is a nice pattern that does extend. So if we just saw that y equals x cubed, its derivative is 3x squared, well, how does it get there, right? How you want to imagine it gets there is through 2 steps. One is that the power of 3 hops down to the front, and then the second thing is that we decrease the power by 1, giving us 3x squared. And actually the same thing happened for x squared. It's as though when we differentiated this, the 2 hopped down, then the power decreased by 1, giving us just 2x to the power of 1. And of course we don't need to write the power of 1, so that would just be 2x. And so the same thing can happen with higher powers as well. So if we had x to the power of 4, the power of 4 would hop down to the front, then would decrease the power by 1, giving us 4x cubed. And likewise for x to the 5, the exact same thing happens. The 5 hops down to the front, the power drops by 1, giving 5x to the 4. And I am repeating this a lot because you'll be using this a lot for the next little while. Okay, so it's good to get as comfortable with this pattern as possible. And this gives us the power to differentiate a couple of other things that might not be as obvious at first. So for example, you could get 1 over x, which doesn't look like a power of x at first, but hopefully you remember it's actually x to the power of -1. So the exact same thing happens to it when you differentiate. The -1 hops down to the front, then we decrease the power by 1, but be careful here because it will now be -1 minus 1, which is -2. And it's polite to rewrite this as a fraction, so the -2 power kicks the x squared to the bottom, then -1 joins in. Okay, and so that's going to give us this -1 over x squared thing here. We could also do the square root of x, noting that this is actually just x to the power of 1/2, and we can follow the same pattern again. The half hops down to the front, then we decrease the power by 1, so be careful with the fraction subtraction here. 1/2 minus 1 is -1/2. The negative power again kicks the square root of x to the bottom of the fraction, and then the half joins in there. Okay, so hopefully the pattern here is clear. Given any power of x, say x to the n, if we want to differentiate this guy to get the gradient function, we grab the power of n, drop it down to the front, then -1 to the power. And so to be more precise, 2 things happen. First, we multiply by the power, then we decrease the power by 1. And that's as simple as it gets for how you differentiate powers of x. Now, you might notice that, quite strangely, I haven't given a proper proof of this, right? That the pattern always works. And the reason is because it's not actually the most simple proof if we were to do so in all generality. Okay, so algebraic tricks, expanding brackets and limits and stuff, they only really take you as far as integer powers go, or at most fraction powers. Once we extend to this working for all possible powers of x, which it kind of does, we need some stronger tools, which we will eventually acquire, but probably not the discussion for right now. Okay, so that's all for this one. Thanks for watching. See you next time.